Hello, so this is my Lab 2 charge tape revisited. So in this lab, we looked back at what happened in Lab 1, and then we reanalyzed it with some different code and a different method. So here's the table of contents. And so the purpose of this lab, again, was to look back at the main experiment conducted in Lab 1 and to reanalyze it with a different method of analysis. And we had to do a lot of recalculations of different pieces of information. And after these calculations, we developed a new computational model which displayed basically an evenly distributed charge across the tape, as that was the method we were using this time to calculate both electric force and electric fields. So first, the lab one recap. In this lab, we just prepared charge pieces of Scotch tape, put the pieces together, rip them apart, analyze the resulting forces. Then we determined remaining charge and tape. And then after looking at these physics concepts, we attempted to make tape float with another piece of tape and then did a bunch of calculations there. The concepts that we have used in both labs were the electric charge, which is just the actual charge that objects have due to certain things in their environment. Polarization, which is charged objects acting on neutral objects and turning them into other charged objects. We have Coulomb's constant, which is used in a lot of the formulas we have to use. Electric forces, which are the actual forces that the pieces of tape are using on each other to cause the tape to either go up or go down, to counteract the force of gravity, things like that. Electric fields were a major concept that goes into electric forces. Um, and we had Newton's second law, which is force equals mass times acceleration. That's used to help calculate force of gravity, F equals mg. And then the big thing that this lab covers is electric fields of distributed charges. Distributed charges can we looked at electric fields that were created by distributed charges in this lab, and we had a bunch of different points on each piece of tape that we used that we like, calculated the electric field from, and then we added those all up to get the net electric field, and that's what we put into our force. So the system and surroundings. The system is the piece of tape we are attempting to float. The surroundings are what the things around it, and the secondary tape we put in close. The initial conditions are a mass of 0.2 grams, and the distance being 0.027 meters. So a preview of the results. The main piece of tape went slightly upwards in the original experiment, and when the secondary piece came close, and this means both pieces of tape received a similar charge, resulting in them repelling each other. And from the code, we saw that electric force and gravitational force were fairly equal when the tape was floating, as there was an equilibrium, and we represented equally distributed charges in the tape and used that to calculate electric force. So in the experiment, we have the net force is positive at first as tape B is pushed up, then it gets into equilibrium, so the net force is zero. The objects exert vertical forces, and the things that exert vertical forces in tape A are on tape B are the tape A and the Earth. Here are the calculations. This was used to calculate point charge in the computational model now. Here is the code for the computational model. We have the various constants. We have the mass and the q that we calculated before. We have our E field function. We have the line charge function. And then we have the actual pieces of tape. We have 100 points for each tape. We have the calculation of E fields and then the force for this whole system. And then we display it. And then here's the program now. You can see the forces and the electric field all coming up from the top tape. There's some similarities and differences between the lab experiment and the actual code. We saw that the force was created due to built-up charges and polarization, and tape pieces repelled each other, resulting in a floating piece of tape. And we saw that the charge was distributed throughout both pieces of tape in both situations. The differences were that we saw the tape measured for the computation model and the actual change of position. That position probably differed, and then more room for human error was there in the experimental situations. So some possible sources of error include accidentally touching the piece of tape before putting it close to objects, tape failing to receive charge from base tape, measuring size of tape incorrectly. The charge was dispersing to other contacted objects potentially, or we just incorrectly measured the amount of tape displacement. And so some discussion. If we had modeled each of our tapes as a single point charge, we would have saw that the electric field is larger when the single charge is used to represent each piece of tape, because the electric fields from different parts of the line point in different directions, and because they point in different directions at different parts of the line, a lot of the electric field is actually canceled out from those different points, and as a result, we have a much smaller net electric field than with the point charge. And so we saw single point charge models concentrate objects' entire electric charge in one specific location. And it's inaccurate because of how charges are actually spread throughout an object. And having multiple points representing each object more accurately shows variations in electric field, more accurately represents the real net electric field value. So conclusions, we saw that opposite object charges repel, charges polarize uncharged objects, charges dissipate into other objects when contacted. And then the big things from this lab specifically are that the lines of charge show how electric fields change at each point between two charged objects, and the lines of charge better represent the actual electric fields of objects and electric forces they apply on each other. Thank you for watching.